Today we are going to think about rays of light and how they move through converging and diverging lenses, otherwise known as convex and concave lenses. Let's get straight into it. To work out what sort of image is formed by an object at a certain distance from a lens, we need to know the focal length of the lens, and that's indicated by the plus symbols in these diagrams. And then we can sketch three rays. The first ray is a ray parallel to the optical axis, which passes through the focal point on the other side of the lens. The second is a ray that passes through the focal point on the same side of the lens and emerges parallel to the principal axis or the optical axis on the other side. And the third ray is the easiest, really. It heads directly towards the center of the lens and just continues with no deviation, no change in direction. First of all, I'm going to do the parallel ray, and this worksheet, which was not made by me, is absolutely fantastic. I love it. We can just draw a line which is parallel here, and I'm just put a little arrowhead. Like with all rays, we want to show which direction the ray is traveling in, and for this next part I'm going to go through the focal point, and I'm just going to keep on going for a long way because I don't know exactly where things are going to work out. And for the second line, which I will perhaps do in red, this one went through the first focal point. So it went through the first focal point here and up to the lens. And then after that it goes parallel. So something like this. And again, I'm just going to put a little head on that to show where it goes. And then finally, the final ray, it just goes straight through in a straight line, straight through the middle. So, like this. And I'll put a little arrowhead on there. And you can see that all three of our rays, when they go through the lens, they converge on this point here. Oh, I think it's this point here, yeah. So let me get a different color. We can actually say that this arrowhead in the object is focused here. So that's the arrowhead, and we know that light that's going from the base of this object would just pass straight through the center of the lens and then go to there, which would be the base of the object. So in this case, we can see that the image is smaller, it's inverted, and it is a real image. It's not a virtual image because these are the rays of light that are meeting at this point. So I'll write that down. It's real, it's inverted because it's upside down, and it's smaller. Okay, let's do the second one. So this is what an object that was greater than 2 focal lengths, and let's just keep on going. So for the second one, I'm going to try and do this. So I'm twisting the paper because I just want to really draw it as accurately as I can. Go parallel up to the lens, and then go through the focal point. Right. Then we go through the first focal point with the second one. Now this is a little bit funny, isn't it? Because we're going off the lens, but we can clearly see where the lens is there, so we're just going to go there anyway. And then we're going to draw a line there. Oh, I forgot to put a nice little arrowhead on for the green. Right, we can already see where this image is going to form because we only really need to draw 2 of these lines. So hopefully our last one will also be the same here. So if we go through the dead center of the lens, I think, yes, I think that's quite reasonable. And we can see that all three of these rays of light meet about here, which I'm just going to draw up to the axis, the principal axis here. The base, any light waves that were going away from there would converge here on that point, and we can sort of see that just imagining one ray of light that's going through there again. But from the tip, any light that's coming away from the tip, and we can just see this, we've drawn 3 examples, would converge down here. So again, we have a real image because this is where the rays of light have met. It's still inverted, but this time we can see this is about 1, 2, 3, 4, and this is definitely more than 4, so it's enlarged. It's got bigger. So that's the difference about the difference that the focal lengths make. Okay, oh, that was number 3. Well, who cares? Let's do number 2, when the object is exactly 2 focal lengths. What do you think is going to happen? We've done larger than 2 focal lengths. We've done smaller than 2 focal lengths. What's going to happen at exactly 2 focal lengths? Well, we can talk all we like, but let's get on and do it. So we've done it a few times now. Drawing the green ray. And then through the first focal point. We're drawing the red ray. Give it a little arrowhead. And then finally drawing the blue ray. Right, and then I can see they all converge here, which I can see is 1, 2, 3, 4 boxes. It's exactly the same as the object. All the rays of light are meeting there, so it's real. The image is inverted, and in fact the size is the same, so same size. Finally, what's going to happen here? Right, well, this is where we are less than 1 focal length. So we draw parallel to the lens first and then through the focal point. Woo! And then, oh, well, this is a little bit strange, right? Because we can't go through that first focal point. Forget it. Let's just do the next one, which goes through the center. So clearly, these rays are diverging on the opposite side, not converging. That's slightly annoying for us, right? So what we actually have to do is we can still do something here. We can trace back this ray. I'm not sure how far I need to go. And we can also trace back this ray. I'm going to draw this like a dotted line because this is not the real ray. But it is where we're getting some convergence here. And they're meeting about here. So I'm actually going to draw, this seems to be where we're experiencing this. Okay, so these rays of light are meeting here, and so what on earth is happening here? Well, let me just explain this, but first let's just think about this image. So this image is not real because these are not the real rays of light. So firstly we need to say this is a virtual image, and secondly, the image is not inverted, it's upright, which is another different thing from all of our other diagrams. And finally, the image is enlarged, which might give us a clue to where we would see this. So if I draw an eye, if you were looking through this lens, you might be looking at something small. This is the real thing. It could be a bug or something like that. But what you would see is this. So if you're looking through this lens at something small, that small thing would appear much bigger. And so in this case, we can see how we're using a convex lens as a magnifying glass, essentially. And we need to put the object that we're looking at closer than the focal length of that lens. And then as we look through the other side, we will actually see something that appears to be much, much larger. Okay. This is the converging lenses. Let's move on to the diverging lens. Before we get into drawing our pretty pictures, let's go over the rules for drawing the three rays for concave or diverging lenses. Firstly, a ray parallel to the optical axis emerges as though it was coming from the focal point on the same side. Secondly, a ray that is heading towards the focal point on the other side of the lens emerges parallel to the principal or optical axis. And finally, a ray that passes through the center of the lens and continues with no change in direction or no deviation. It's still parallel to this optical or principal axis. But when we get to there, with the converging lens, if we had, say, another ray of light here or another ray of light here, they would all start coming together. They would converge on the opposite side. But here, because this is a diverging concave lens, they are completely the opposite and they want to go the other way. So we use the other focal point and putting our we can know that the light would go like that. Now this is going to be annoying if the light just keeps diverging, but let's keep on going and do that anyway. So the next one is a ray that is heading towards the focal point on the other side of the lens, and it emerges parallel to the optical axis. So in this case, our green line is heading as if it's going towards this focal point on the other side, but when it emerges, it's just going parallel to the optical axis. Okay. And then finally, the center ray is a ray that passes through the center of the lens with no change in direction. So that's something we already saw. I haven't drawn any arrowheads here, have I? Okay. We can see, oh no, we can see that all of these rays diverge, so they're not going to meet. So once again, we have to backtrack the rays from this lens. So let's backtrack the red one. We just need to do it really until it crosses. And because this is not the real ray, I'm going to do it as a dotted line again. And we can see now that the red line crosses the green line and the blue line in different places. But of course, we still need to backtrack our green ray. Okay, got it. The thickness of the pen is something to take into consideration. And here we can see that there is a meeting point for all the rays. So, as with the others, we had our object, and we've discovered that the image in this case is here. And this is our image. And the image is formed not from real rays, but from virtual rays, so it's a virtual image. In this case, it is smaller, and it is also the same way up as the object, so it's upright. Well, I hope that's been helpful, just to think about converging and diverging lenses, and also drawing ray diagrams. I think it's really cool. I think this is a fun little science thing that you can do, and it's an opportunity to use different colored pens and show something of your artistic quality, or something like that. Okay, so have fun drawing the diagrams for rays in lenses, and thank you for watching.